Okay, so now that we are done with the mathematical preliminaries, I guess I'll brush up for linear algebra would be great. So now we can move on to the deformation of solid body. So we want to model how a solid body would deform after, like, basically, like, we want to solve the equations which would give us how a solid body would deform. So basically, let us start with defining a few things. So basically, this is my body, and like I have this rp, like I have this all this vectors, like rp naught would basically give me the direction of the vector p naught. So like I can basically write this. Let us say that after deformation, let us say that after deformation or like new configuration is of this, basically this p naught would be something p. And so basically our rp naught was initially this vector, right? So after like deformation, it goes to this point p naught where its new vector is r. So this new vector is rp. So basically what I can do is I can define this displacement vector, this like up vector, as this r of p, like this current vector minus the additional vector. So basically it basically defines how it displaces. So like if I tell you at if you are at rp naught, then basically if I give you this up vector, then basically like you can basically go in that direction and you would be at the final position of p naught after deformation. So let us say that there's this, like, we don't know what UP is, right? I mean, we don't know what UP is at every point. Our goal is to basically find that UP at every point. So basically, I assume that UP is like it's a displacement at every point. So basically, I assume that UP is a vector field, displacement vector field. Like at each and every point, I have this vector field U, which is the displacement vector field. So like if I am standing at this point, I know the displacement vector field. I can basically go to that point from that point, and I will know that this is the final deformed configuration of this. So basically it's a displacement vector field, and it is a function of initial coordinates. Like if I give it that I'm standing right here, that at this point it would be some vector, and if I go along that vector, I would like reach the final, like the after deformed position of that point. So now that we have this function of it, so we can basically write this as like our new coordinates x1 bar as x1 plus times u1 of like, I mean, the u1 is the u1 function, like as like you know that u is a vector field. So u is consists of basically three functions: u1 I cap plus u2 e2 cap plus u3 e3. So basically it's the I1 function of this displacement vector field, where u1 is a scalar function. So basically, we'll know the each and every position of like of every point, yeah, the final position, if we basically know the u vector field. So basically, to find the u vector field and the stress and the strain we are talking about, so we can basically what we can do is we can consider another point q in the neighborhood of p. So basically, Q is a point just next to P, and like we can say that P naught Q naught, like P naught Q naught is basically del one even cap, del two E2 cap, and del three T cap. So basically, the coordinates of Q in this case would be, yeah, would be x1 plus del 1 e1 cap plus x2 plus del 2 e2 cap. So basically this would be the initial position rq naught. So like obviously let q naught move to the final position q, so that its displacement like at q would be the displacement vector field value would be the vector which is like its value at x1 plus delta x1, x2 plus delta x2, x3 plus delta x. So we know that, right? So basically, it's just basically at a point just around in the vicinity of, yeah, at a distance x1, x2, and x3, like del x1, del x2, and del x3 from this. So basically, we know that u of like this u of q is basically it's a as like right here, basically it's like at each point of the vector field, its component are like, I mean, we have the vector field, displacement vector field is consists of u, right? So at each and every point u1, u2, and u3, at each and every point of u1, u2, and u3, it's x1 plus delta x1, x2 plus delta x2, x3 plus delta x. So we can, like, for each functions u1, u2, and u3, we can basically write the Taylor series expansion to find its value, since like u1, u2, and u3 are scalar functions, right? So basically I can write this ith component of vector field u as u of x plus del 1 plus u of x plus del 2 plus u of x plus del 3 as the u of x1, x2, and x3, the like u at x1, x2, and x3. And I can basically write the Taylor series expansion, like I can take the derivative del u upon del x1 times delta x1 upon del u1 upon del x2 times delta x2 upon del u1 upon del x3 times delta x3. And the same thing I can write for u2 too, like u2 at this slight point q is equals to u2 of this plus del u2 upon del x1. Like I can take partial derivative with respect to x1 and multiply it with del x1. I can also take partial derivative with respect to x2, so like del u2 plus del x2, and so on again for this. And in a similar way I can basically write that for u3 too. So like I basically found this u1, u2, and u3 in terms of the original vector. So like the u1, u2, and u3 values at q, I have basically found them in terms of p. Like the ux1, x2, ux1, u of x1, x2, and x3 is basically the u value at p, right? So basically now we have this thing, right? So we have this u of q vector. So u of q is basically the vector field at point q, and I have this vector field at point p, and I can basically write this as something e1 cap, something e2 cap, and something e3 cap. And obviously, like this e1 cap, e2 cap, and e3 cap, I can basically just take this at the other point, and I can basically define that there's since q is at a distance of del x e1, del x e2, and del x e3 of p, so there is this small change in the vector field too. That the del u is a vector, and that is the change in the vector field once we go from p to q. So basically, I can define as del u as del u1 times like as a vector del u1, del u2, and del u3, and I can basically, since we wrote this exactly above, that u1 is equals to del u1 x1 times del x1 and del u2 x2 times del x2 and all that. I can basically represent this in terms of a vector, right? I mean, I wrote del u1 as basically del u1 del x1 times del x1, I del u1 del x2 times delta x2, del u1 del x3 times delta x3. So basically, we multiplied these two terms. So basically, it's the same thing as before. It's just represented in terms of matrix multiplication in this case. Yeah. So and the last time, like we had this del u is equals to some this matrix times del x. So what I can do is basically I can very cleverly define this as a tensor known as the gradient of vector field. Like we have known that there's a divergence of vector field, but we have never heard of a gradient of a vector field. We always known the gradient of a scalar field. So basically this is a gradient of a vector field, and this gradient of a vector field is a tensor. So if I give you at some del x point, so it can give me del u tensor. Like if I have this del x tensor, like del x1 plus del x2 plus del x3, then this gradient of u tensor can give me the del u tensor, like I mean the del u vector. So basically, this del u grad u is a tensor, and this is also like pronounced as grad u, and it's basically a transformation. So it's basically takes this del x vector and it transforms it into the del u vector, and like it's the same as the matrix which we wrote in the previous page. This is the same as the grad u tensor. It's just basically we are defining it at this point. So basically, now that we know it's like basically some like it's sort of bookkeeping, and like we basically in the end we what we have is we can basically define its component as the component ij of this grad u tensor is basically times del u times del xj and times ej cap. So if you like basically if you don't understand this, what's the key takeaway is that del u of I of j is basically this thing. So like if I have to write this grad u times like the 2 1th component, so basically the first index is del u2 and the second index is upon del x1. So basically this 2 corresponds here and this 1 corresponds here, and grad u of 2 1 is basically this thing right here. So basically it's grad u2 upon, like it's basically del u2 upon del x1. So basically this is the 2 1th component. So like this is grad u 2 1, and like it's basically just we're basically defining each element at this point. So basically if I want to represent this as a matrix as whole, so like if I want to write this in index notation, how can I write this? Is basically I can write this as grad u of ij is equals to uh, just a second. I can basically write grad u of ij is equals to del j times ui. So basically this one was basically ui and this is basically grad j. And so like that's basically a very simple concept as such. There's no like a lot of bookkeeping for this. So basically it's the same, like we're just basically formally deriving it right here, like how exactly did we get this. And it's also very simple, like basically you are just, as like we did in linear algebra, we're just basically mapping where it goes the unit tensor. So like if you wanna like understand more about this, you can basically just go through this proof. And like I'll not go through that. So basically, as I said before, it's basically uh the same. Like I wrote grad uij is equals to del ui times grad del j, del xj. And like this is basically the matrix representation of this. Like if I know this, the indexes, like if I know at each index what its value is, I can basically write the matrix for that too. And like basically this is the matrix representation for that. And like obviously you can basically, so this is basically known as the displacement gradient tensor. This matrix is known as a displacement gradient tensor. So now that we have this UP naught and UQ naught and all that stuff, we know that grad U is equals to UQ naught minus UP naught, right? So basically, I can write this as RQ minus RQ naught upon RP minus RP naught, right? So basically, I have this grad U tensor is equals to RP minus RQ. So basically, the final position of P and Q. So RP minus RQ would be this P final and Q final, and so this vector minus they have this original position. RQ naught is the original position of Q naught, so this is Q naught, and let's say this is P naught. So basically this is, so basically we have subtraction of two vectors is basically giving me this grad U vector, or like this delta U vector as such. So basically it's the same as the like vector representation of this. So like as said in the last page also, I can like basically we can basically prove that this is pq vector minus p naught q naught vector, as like I did this in the last page. And like basically if you want to check the diagram too, we can basically check the diagram right here. So this is this del x vector and this is this. So delta u, I know that I can write this in terms of del x vector, and like as we know that we represented this like this del x vector as like the vector joining p naught and q naught. So like p naught q naught is also del x, and like I can write del u as grad like this tensor times this delta x tensor. So basically I know that if I take any point pq, so like the final position of pq after this some share or strain or whatever that may be the case. So if I have this initial P naught Q naught, I can get the final PQ by just considering this grad U tensor. Like I have this, if I am given the displacement field, I can take the grad U tensor. I can also add the identity vector. And basically, if I have this P naught Q naught, suppose I can take any 2 points P naught and Q naught. I have this vector. I know exactly where exactly how like how exactly will this PQ vector be oriented after like transformation. Like if this P naught Q naught is oriented to something this q and p, I know exactly how this pq and p naught q naught are related in terms of this displacement gradient field. So like it's basically very simple. You basically take this delta x at that side and you have this pq is equal to grad u plus I times delta x, and this delta x is basically this pq stuff thingy. Yeah. So delta x is basically p naught q naught. Yeah, delta x is basically p naught q naught. So yeah, it's basically this. And like to avoid the bookkeeping, we basically define this thing as f tensor, or that another tensor. This is also known as the deformation gradient tensor. So it's just basically nothing. It's just basically this another new tensor which we defined. It's basically the grad u plus I times tensor. It's a new tensor f. It's also known as f, and it's like basically the same. So there's just no point in that. Now here comes the important part. So like now that we have all this, we basically know that if we have the displacement vector field, we know exactly how each and every point in it will transform. So now that we know that, how exactly can we define strain and local rotation? So basically engineering strain, we can define it as like this is this engineering strain type of thing. Engineering strain epsilon is equals to half of this gradient of u. Like it's basically the symmetric part of this displacement gradient tensor, right? This is the symmetric part of displacement gradient tensor. And there's also this quantity called local rotation theta, that is half of this anti-symmetric part of this gradient. So like obviously you might be wondering how exactly does this happen. So like there's no need to worry as such. Like it's quite complicated and mathematically intense proof, but basically we can uh, it's like very easy to come out. So basically I'll just give you a geometric feel for that. I'll not go over the proof. I can just basically tell this that epsilon ij, like the ij component of the strain, is basically equals to half of, like obviously epsilon ij would be like half of grad u plus like this grad u times transpose. And so like you can say that del ui upon del x upon this is the transpose del uj upon del x. So like then in comma notation, I can like basically write as u I comma j plus u j comma I. So basically this is the engineering strain tensor. So basically engineering strain tensor is like obviously since it's symmetric part, then epsilon 1 2 is equals to epsilon 2 1. And like engineering strain is basically, if I were to say geometrically tell you what exactly is engineering strain and why exactly is it a tensor. So let us consider a planar problem. Like let's just consider 2 points. So basically, I have this PQ vector and I have this PR vector. And like let's say that PQ vector is like going in this, like it transforms to something like this, and PR vector. So the XX part or the epsilon 1 1 part or epsilon XX part is basically tells me how exactly is Q like PQ changing. So like it's basically the same as PQ minus P naught Q naught. Like this is the final PQ minus P naught Q naught. This is a change in length in x direction. Like it was initially in x direction, but now it's finally it has this some length PQ, and this is upon initial length like P naught Q naught. So this is like engineering strain in x direction. So similarly, I can define it in y direction, and that I would denote as epsilon yy or epsilon 2 2, or that component of the engineering strain tensor. So epsilon 2 2 is basically P naught R naught, and like I can basically write this as PR minus P naught R naught upon basically the same as P naught R naught. So basically, this is the change in length in y direction upon the original length in y direction. So basically, that you might get the feel why we are basically representing engineering strain as a tensor, because there are a lot of components of engineering strain as such. Like there's this x component, there's this y component, there's also this xy component of engineering strain, which basically defines how much angle it has changed. So like our initially PQR was like this, finally PQR is something like this. So basically it has changed an angle alpha 1, and this has changed an angle alpha 2. So this alpha 1 plus alpha 2 is basically the shear strain, like how much it has sheared itself. And that is basically how we define epsilon xy. So this alpha 1 is basically epsilon xy, and this is also alpha, it is also epsilon xy. And like in engineering, there's also this engineering shear strain gamma xy, which is basically equals to the sum of both alpha. So it would be equal to 2 alpha, and it will be equals to 2 epsilon xy. And like basically this is like how we define stress, like I mean the strain components, and these are the basically the strain components as such. And this is how we define, and like these are the like proofs of this. You can like basically go over all of these proofs, like how basically the displacement tensor field and the strain components are related, but like there's no need for going over that proof. So basically, there's this things about these are like the things about the strain tensor. A few points, indeed. So I guess my screen is stuck for a second. Yeah. So these are a few points about the strain tensor. So basically, it is not to be multiplied anywhere, and like it's not to be multiplied anywhere. And like if I have a vector, I can basically convert it into x and y component, and basically I can find the strain of x component and y component of that. And like it is no like if I have the displacement tensor field, then I can basically write this thing. I can basically write this small thing right here, that epsilon ij is equals to half of grad u plus like the grad u plus grad u of transpose and that kind of stuff. And like it's basically very simple, and that's exactly how we relate to that. And like with that, I guess we basically complete the part of our shear strain and like all that stuff in there. Yeah. And like maybe you can just go over through this formula. So yeah, I guess this was like how basically we represent the displacement gradient tensor field, and how we basically relate it to the displacement gradient tensor field and how we relate it to the strain tensor, like the epsilon xy or the strain tensor as such. So yeah, so that's it. I guess in the next video we'll just basically go over maximum strain and like quickly go over through the strain compatibility too.